Hello everyone, Mr. Minix, my name, math is my game. Today I'm joined by my second period Algebra II class. They're excited to be here. It's Monday. We just got off of the stinking weekend or the freaking weekend, whatever you want to call it. Anyway, Chapter 6, Section 8. The title is probably the second most bit of writing that you have to do for this. The title is Graphs. I asked each person who's going to take notes to get some graph paper. Graphs of square root and other radical functions. The objectives, you don't need to write those down. Those are up there so that I'm doing my job. By the end of this lesson, you should be able to identify domain and range of square root functions and of other radical functions given their graph. So maybe we'll try that for our first example, and maybe even our second example. Another objective is by the end of this, you should be able to graph a simple square root function. You should be able to graph a simple other radical function, like maybe a third root function. Also, by the end of this, you should be able to graph a transformation of a square root and or other radical function. Look what it says in bold and underlined. Some people say that's me being mean. If we look at the legal obligation that we have to cover this material, the Common Core Content Standard in that particular standard says that students will be able to do this with using one of these and with using their brain and not one of those. Okay? I know some people rely heavily on one or the other. Mostly the one, the calculator. But anyway, any questions before we dive into this lesson? Okay, here we go. Example 1 then. Example 1. State the domain and range. State the domain and range of the given graph. Of the given graph. So we'll get some graph paper here. So the graph's going to be given. So I'm going to sketch a graph. It's going to look something like this. And it's going to look like that. I would draw this in the notes, sure. Domain and range, it's been a long time since we talked about them, since we'd studied quadratics, maybe polynomials. This particular point here, I'll label it the point P. It has coordinates, it looks like 3 something, huh? So is it 3, 4? So the point P has coordinates 3, 4. Of the very most importance here is this arrowhead and this point. Let's think all the way back to geometry. The point that we see over here, that's not indicative that the graph goes on forever. This arrowhead is indicative that the graph goes on forever that way. Does that make sense? End point, graph keeps on trucking. End point, graph keeps on trucking. So far, so good? Okay. Thinking back to Algebra 1, Algebra 2, Lesson 2, Section 1, the domain is all the possible what? X values, right? Okay. So when we ask the question, what's the domain of this function? When we try to answer the question, what's the domain of this function, or what the domain of this function is, the domain, what we're looking at, is the x-axis. We want to know along the x-axis, along here, along this axis, what values does that function take on? Or what values can it take on? It takes on 3, so 3 is part of the domain. What's that? I'm hearing a negative infinity. That's good. So for the domain, we're saying negative infinity is the smallest it can get. And 3 is the biggest that the domain can be. So what we're using here is a type of notation called interval notation. Now, we do need to close up that with either parentheses, brackets, braces, or something else. We're going to use actually two different symbols. One means that we count it, one means that we exclude it. What do we got? Bracket on the left, parenthesis on the right. That's a really good try, and it is brackets and parentheses. Let's think about what each means. Bracket means that point's included. Parenthesis means that point's not included. So flip it, yeah. So parenthesis because we never get to negative infinity. Bracket because we do count the 3. Nice, good, awesome. I like when people bring their A games on Mondays. Makes my job a lot easier. Good. So that's our domain. Anybody think they have a handle on the range for this one? The domain goes from negative infinity to 3. The range is from negative infinity to 4, negative infinity to positive infinity. How about the range goes from negative infinity up to 4, right? What about our symbols? Going to be the same. Parenthesis, bracket. Does anyone have any questions on that end of this? The range, by definition, is all the possible y values. All the possible y values. Okay? So some of you over the weekend took the ACT, the ACT. Some of you didn't. Circles. Let's follow this up with a real quick look at a circle. Suppose we had a circle, and we're going to be studying this before the year's out. This is the unit circle. Its center is the origin. Its center is the origin, and it has a radius of 1. What do you suppose the domain and the range is of a circle, of the graph of a circle, of the unit circle? What would the domain and the range be for this graph? Positive 1 to negative 1. Now, if you're going to use interval notation, you got to be careful. It's always small number, big number. Always. So negative 1 to positive 1. Parentheses or brackets? Parentheses or brackets? Brackets. Its radius is 1, so it does go through the point 0, 1. And it does go through the point 1, 0, and negative 1, 0. So we do use brackets. So negative 1 to 1. And what about the range? Same thing, negative 1 to 1. Now, some of you are going to be taking that one class next year, that college credit, algebra, whatever. So you're going to be studying ellipses. What if you studied an ellipse that looked like this? And this point out here was like negative 6, 0, and this one was 6, 0. How would that change that? What would change, the domain or the range? The domain would be a little different, right? We feeling all right so far? Good. Good. Question. If the domain was range changed, wouldn't the range change? So this green thing that I tried to graph, and apparently I'm not very successful at it, what I tried to do is sketch this green graph in a manner such that its maximum value was positive 1, its minimum value was still negative 1, but it went a little bit further over on the ends. So it's an ellipse like that. Okay, so because of that, it still has the same domain and range. If it were squished a little bit or even stretched out, if it were stretched out like that, then its range would change. But as drawn, its range would have stayed the same. Okay, good question. Okay, so we've got an idea of what domain and range are. Now it's time for something new. Another new parent function. Yay! Well, all this talk about domains and ranges and functions is making me thirsty. I could go for some pop right about now. Um, you know what state has the smallest pop, don't you? Minnesota. Minnesota. That one was submitted by. That was pretty good. That was good. Okay. I lost my marker cap. I dropped it as if it were hot. Gonna go nuts looking at it, looking for it. Okay. So here we go. Y equals the square root of x. Y equals the square root of x. Back in the day, I asked you to memorize 3 parent functions. Anybody remember the 3 I asked you to memorize? I said at any point during the year, expect a quiz over these 3 graphs. I'll give you a hint. I'll tell you that they're already on the chalkboard. Y equals the absolute value of x. Y equals x to the squared. Y equals just x. All of those go through the point 0, 0, and 1, 1. 0, 0, and 1, 1. It seems as though just about any graph that has a y and an x in it, and it's not translated or anything like that, will go through the point 0, 0, and 1, 1. This is no exception. So let's generate a table of values here. X, y, which is the square root of x. What's the square root of 0? What's the square root of 1? There's got to be at least 2 more points that'll fit on our 10 by 10 graph paper here. What's another integer pair of points that'll fit? I heard 0, 4. We're kind of on to something. The square root of 4, which is 2. So how about 4, 2? And then 1 more that'll fit on our 10 by 10. 9, 3. I would commit those 4 points there to memory. Those are 4 points that this function passes through. Make sure you know them. Make sure you know them. So the question is about these functions. Those all go through 0, 0, and 1, 1. Yeah. Okay. All right. Well, what ends up happening here might shock you. Maybe it won't. So we're going to go through the origin. We go through 1, 1. We go through 1, 2, 3, 4, 2. And we go through 9, 3. Now, I need some kind of writing instrument to fill this in. I'm going to use a crayon. I'm going to use a crayon. I'm not very good at staying inside the lines. I would write that graph on your graph paper, yeah. So what's real important here is what happens over here and what happens right in there. Remember, our graph paper only goes out 10 units, but we know that the square root of 16 is 4, and the square root of 900 is 30, and that we could have points in between there. They just wouldn't be integer points, right? So what do we think is going to happen on that far extreme right end in the green box? Is the graph going to keep trucking, or is it going to stop? It's going to be an arrowhead. Awesome, absolutely. Arrowhead, because the graph keeps on trucking over there. Okay, so that is an arrowhead. So if we're thinking about the domain and the range, we could already start to fill in the upper end of both. Yeah. The question is, do we do the same thing on the other side? We'll answer that in a second. So let's go ahead and talk about the domain. The largest x value that this thing's going to take on, it's going all the way to infinity. And it never gets there, so we use a parenthesis. As far as the range goes, the graph's going up, but it's not going up as fast as it's going right, but it is still going up, right? So the range is also going to go all the way up to infinity. So now the question is, maybe I should ask it in Spanish. Maybe I should ask it in Spanish. ¿Qué pasa? ¿Qué pasa aquí? ¿Qué pasa aquí? Pasar is the verb to occur or to happen. ¿Qué means what? Aquí means here. What happens over here? Let's take the square root of -1. What do we get? An imaginary. We're graphing something in René Descartes' Cartesian plane, which is comprised of a number line comprised of real numbers. So what happens? Nothing. Nada. So, back to the question. So what happens in that little star area? It's an endpoint. There's no arrowhead. It's an endpoint. It's an endpoint. So the domain and the range then both start or begin at 0, and it's a bracket on those. Okay? What do we think? Does it make sense? Does it seem logical? Logical? It reminds me of that one time I went to the psychic medium who went to jail but escaped. She was a small medium at large. She was only like 4'7". Example. Let's try to graph y equals negative the square root of x minus 3 plus 2a. So the interesting thing about people who have a gift to see into areas that we can't see, and some people I believe really do have that gift. I think some people just want your money, and they have like a a crystal ball. But I think some people really do have a gift to see certain things, but they listen. And I think Algebra II students who say they can't graph these without a graphing calculator, I think they're lying. They just don't listen. There's three parts of this expression. There's three parts of this expression that are all telling us something about how the graph compares to the parent function, right? We know what the parent function looks like. It begins its life at 0, 0, goes 1, 1, 1, 2, 3, 4, 2, and 9, 3. The parent function does that. The function we are asked to graph is going to look very similar. It's going to look very similar. I need to switch colors. What color should I switch this up to? Blue? Y equals negative square root x minus 3 plus 2. All I'm going to do is copy that. I'm just going to copy that. Look at that. There's three different things that are telling us something. Let's see what we remember from transformations. What do we got? 2 is the y value, so the graph is going to be translated up to, question? It's the same function, yeah. If we look at the root of this, if we were to take this blue thing and we were to kind of forget about this minus 3 and this plus 2 and this negative here, we're graphing the parent function. But it's just being modified a little bit. The plus 2 on the end of it, tells us it's translated up 2 units, right? Okay, so with our blue graph, we could just translate it up 2 units. Yeah, but don't stop there. Tick tock and you don't stop, and to the tick tock and you don't quit. I'm not going to say the rest of it. What about the minus 3 inside the grouping symbols? It translates it to the, it's either to the right or to the left. It's counterintuitive, so it's to the right. So the graph gets translated to the right 3 units. Okay, so it looks the same, but it's up 2 and 1, 2, 3 to the right. Now that's not the whole story. The negative tells us it's not up 1, it's mirror, mirror on the wall. It's flipped over or reflected across the x-axis. So because it's reflected, I guess we got to flip this thing upside down. Oh, let's try that again. Okay, so it's going to be a reflection. If it were a reflection and it started there, it would do that, but it's over, we said what, over 3 and up 2. Now I know what you're thinking. You're thinking, but Mr. Minnick, we don't have the smart board in our notebook. You're right, you don't. But you do have 4 reference points that you can base this off of, right? You start at the starting point. Relative to the starting point, what do? Over 1 and up 1. Or, since it's a reflection, over 1 and down 1. So that's why it's real critical to understand how to graph given a parent function. We ready to try another one? So I think if we look at another example, this is going to clear some things up. So let's try this. Example. Graph y equals the square root of x minus 5. The question is, could we use a table of values method? Absolutely, positively, 100%. Some people like the table of values method. I'm not a fan. I'm a fan of understanding the parent function and basing things using transformations off of that. I know Mr. Jones likes the table method. Okay, here we go. Graph this. So let's answer this question. What's that minus 5 tell us? The graph is going to be translated down 5. So rather than starting at the origin, we're not going to be starting there. We're going to be starting where? Down 5 units. Down 1, 2, 3, 4. Right there's our starting point, right? Relative to that point, let's think. We go through 0, 0, 1, 1, 4, 2, and 9, 3. So relative to that, we're going to go, well, relative to this point here, we're going to go 1, 1. So if we pretend like that's the origin, and we start it from there. So you go over 1 and up 1, and over 1, 2, 3, 4, and up 2, and over 9 and up 3, and then that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 1, 2, 3, and that's it. And that's it. I think that's a lot easier than the table method. That's it. Question. Find its starting point. Find its starting point, and then you just yeah. That's not that bad, is it? Let's try one that's about to run a 5K. What would you do before you ran a 5K? Oh. Let's try this one. This one's about to run a 5K. So where does this one begin? Is it translated to the right or to the left or up or down? No, it's not. So this one begins right at the origin. Now what's that 3 tell us to do? It tells us all the y values are how much bigger? Are 3 times bigger. Are 3 times bigger. So let's think about this. We were 0, 0. 0 times 3 is still 0, right? So that one stays the same. Now the 1, 1, it's 1 times 3, so that's really 1, 3. So instead of going here, it's over 1 and up 1, 2, 3, right? So it's going to be taller. Okay, let's keep on trucking with this. We went through 4, 2, but that y value of 2 is getting tripled, right? So it's really going to be 4, 6. So over 1, 2, 3, 1, 2, 3, 4. Not 4, 2 like normal, but 3 times higher. 3, 4, 5, 6. So it's going to be taller. And then the 9, 3, what's that 9, 3 going to be? 9, 3 is going to be 9, 9, right? So there it is. That's it. That is it. What do we think? Got him? So you're probably thinking, well, is that it? It's got to get harder than this, right? Could we handle another new parent function? One more. One more. And then we look at a new parent function. I'm going to make this one purposely challenging. I saw a guy that looked just like Peter Griffin yesterday, no lie, at the laundromat. Okay. So, you had a really good student teacher this year who taught you the F word. Had a factor. What can we factor this expression into? What could we factor out of that expression? We could do better than a 5. We could factor a 25 out of that, right? When we factor a 25, that's going to leave what? X plus 3. Now, we learned from our square root rules that we could split apart the square root of a product, right? Well, what's the square root of 25? Oh, so this is y equals 5 times the square root of x plus 3 minus 2. So now we know the y values are 5 times bigger. The graph begins its life not at the origin, but translated down 2 and to the left 3, right? So to the left 1, 2, 3, to the left 3, to the left 1, 2, 3, and down 2. So that's where the graph starts. And our y values are 5 times taller. So not over 1 and up 1, but over 1 and up 1, 2, 3, 4, 5. Not over 4 and up 2, but over 1, 2, 3, 4, and up how much? Over 4 and up 10. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10. So this graph is going to look like that. What do we think about that one? You know what we just did with that? We covered the second content standard. Rewriting the given expression by factoring something out of it. The starting point there is -3, -2. Yeah. Okay. So the starting point is -3, -2. Okay. So I've got to show you this new parent function, and I've got to give you a disclaimer about it. Not a chuck-claimer about it, but a disclaimer about it. Okay? Another new parent function. Here we go. Y equals the third root of x. Now we saw all those other parent functions go through 0, 0, and 1, 1. Guess what this one's going to go through? 0, 0, and 1, 1. X, third root of x. What are some other integer points that this might go? There's only actually one more that's going to fit in the first quadrant. 8 what? Nice. 8-2. Good. 8-2. So, a needle pulling thread, la, a note to follow, so, and tea I drink with jam and bread. And that brings me back to do. A deer, a female deer, ray, a drop of golden sun. So we do know that the cube root of 216 is 6, and the cube root of 512 is like 8, and the cube root of 729 is 9, and the cube root of 1,000 is 10. What happens on the right side of that graph? Does it keep trucking? Keeps trucking. Does the other one stop? Let's ask the TI Inspire. You ready? Let's ask the TI Inspire. Oh, TI Inspire, would you please graph a third root of x for me? Please. Please. It's lying. The mighty TI Inspire is lying. It's lying. It's not as good for graphing these as the old school TI 83 plus. Let's graph a third root function on this. How did we get to all this stuff? Well, I'll show you in a second. Do you see how it goes on in the third quadrant? Because -2 times -2 times -2 does equal -8, doesn't it? You can take the third root of a negative. Do you remember that lesson from a couple weeks ago? You can take the third root of a negative number. So the deal is the calculator lied to us. The graph does go through here, and it does go through here, and it does keep on trucking this way. So let's think about the domain and the range of that real quick. Is the domain restricted at all? No. So it goes from negative to positive infinity on the domain. And how about the range? Same thing. The range also goes from negative to positive infinity. So where did the TI Inspire go wrong? It thinks you can't take the third root of a negative, but you can, because somebody in here got into the document settings, and somebody set up the document settings to handle complex numbers. If you change it back to real, then it can do it. But remember when we took the square root of -1, and it couldn't do that? So it can't do that now. So you have to really be familiar with the operations of it, like with its features and whatnot. It's kind of like driving a four-wheel drive. Anybody ever drive a four-wheel drive and it's snowing out and you can't figure out how to put the stupid thing in four-wheel drive, so you're just spinning your tires? The calculator's the same way. You got to know how things work. So, we're almost done. Almost done. Are there any questions, comments, concerns, short debates about that one? Is that going to be the only parent function we can plug a negative into and it works? If we're talking about root functions, let's get something straight right now. The square root of x looks like this. The fourth root of x looks virtually identical. The only difference is it goes up a little higher here, and it does that. Okay? If we were to look at a sixth root of x, it looks similar, but it goes up a little higher still here, and it goes like that. So any even indexed root function will operate or behave the same way. What about odds? Let's look. The third root of x looks like this. If we graph the fifth root of x, it's going to look like this. If we graph the seventh root of x, it's going to look like this too. They just get a little squarer. You got it. The evens have a stopping point and the odd ones don't. Okay? So, last one of the day. Here we go. Example. Let's try to graph y equals -1/2 times the third root of x minus 2 plus 7. So This isn't really a starting point or a stopping point, but it is a point of reference. It could be thought of as the center. So let's think about our center of this graph. Where would our center be located? Not at the origin for sure, right? But it's going to be to the right 2 units and up 7, or yeah, up 7. 1, 2 to the right and up 1, 2, 3, 4, 5, 6, 7. So relative to that point, it's kind of like now, it's kind of like we're going to be graphing that, right? But hold on, wait a minute, Mr. Postman. It's a half, so it's going to be shrunk. The half tells us it's going to be half the height. And what about the negative? It's going to reflect it, right? So let's think about this then. Instead of going over to the right 1 and up 1, or instead of going over to the right and down 1, we're going to go over to the right but down a half. If it were the square root of x, or the cube root of x, it'd be over 1 and up 1. If it were just a negative, it'd be over 1 and down 1, but it's a half, so it's over 1 and down a half. Symmetry, over the other way and up. And then what was our other point? It was 8, 2, right? Over 8, so it's going to be half of 2, so 1. So let's see, over 1, 2, 3, 4, 5, 6, 7, 8, and up 1. So it's going to do something like this, like that. There it is. We feel all right about those? Think we could handle that with and without a calculator? I got 3 of them for you, 3 or 4 for you to try tonight. Okay. It's been real, it's been fun. I don't know if it's been real fun. I hope everybody has a terrific Monday. I almost said terrific Tuesday. See you next time.
Good.